What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. I got a rock.
So yeah, there's a question. There's a question on homework 1 here. Give an example of a directed graph whose DFS tree has all 4 possible edges. You can name it A, B, C, D if you want to, and then just say we'll start at A, and then we'll go in lexicographic next order. Right. So I mean, as long as you are stating your assumptions and they're reasonable assumptions, then yeah, that's cool. Yeah, go ahead.
Well, what does it mean to, on question 3, what does it mean to have, what's the degree of the vertex?
So the degree of the vertices is the number of edges incident on it. So, for example, if I have, well, here, let's take the, let's see, I don't know, this graph here that we've been working with. What's the degree of each vertex? So I has degree 2, right? Why? Because there are 2 edges that are incident on it. The degree of, say, C is going to be 1, 2, 3. Right? You can have a degree IJK X over here. You can have a degree 0 vertex, right? It's an isolated vertex. Right? Otherwise, the degree could be 1. If, for example, like this, right? The degree could be at most from 0, 1, 2, ... What's the maximum degree that a vertex could have in a graph with n vertices? In a simple graph with n vertices, right? So if you're one vertex, you can connect to n minus one other vertices. And so you don't connect to yourself because that would mean that you're allowing self loops, which is a kind of graph, but it's called a pseudo graph. Right? Okay, does that answer it? Okay. Any other homework questions this Friday? Yeah, go ahead.
For number 2, you give pseudocode.
DFS can be used to determine if two vertices are connected. Develop an algorithm, yeah. So develop an algorithm means give pseudocode.
Okay. So is the idea like, as long as you have visited in your, you keep a list of visited but not processed nodes, and then as long as both existed there, and then you see another visited one?
Well, I mean, you can ask questions, or you can ask questions and then modify the graph, right? So suppose that you ask the question, does there exist a cycle? And the answer is no. Can X and Y possibly be on a cycle? No. So suppose you ask the question, does there exist a cycle? And the answer is yes, right? Well, how do you know that it involves X and Y, right? You could take X out and then ask a different question. You could take Y out and ask a different question. You could take both out and ask another question, right? It's finding the right question, right, to ask, because you know how to use DFS for cycle detection. Right? Okay. All right. So yesterday we were looking at minimum spanning tree, in particular Kruskal's algorithm, right? That makes locally optimal choices by sorting the edges. Let's go ahead and review that really quick, actually. Not on this graph because it is unweighted. You can do Kruskal's algorithm on an unweighted graph. What would it look like? Well, all edges have exactly the same edge weight, 1, right? 1, 1, 1, 1, right? And so there's no, you can consider them in an arbitrary order. And you would start adding them, you know, as long as it does not induce a cycle. So we'll add that one, we'll add that one, right? Now the tree that we've built so far is a disjoint tree, right? Because it is disconnected if you're only considering these highlighted edges. But the second that you add another edge here, maybe it becomes connected. Now, would you necessarily add this edge right here? No, because it would induce a cycle, right? So you don't end up adding that edge, right? And then you can continue. The problem is when you're doing this, as far as the pseudocode goes, here we go. As far as the pseudocode goes, you are asking a question with respect to connectivity, right? You're asking, is this acyclic or not? And from our analysis last time, that means that this is going to be order n plus m. In other words, you're doing a DFS on this, okay? And since you're doing it on potentially order m edges, right? And remember that sorting them is going to be order m plus, or sorry, m log m, right? Well, this is a independent loop down here. So which one of these is worse, right? This one ends up being multiplied together, and so you have order m times n plus m, right? This is the naive way of looking at it. M n plus m squared, right? Now, if m is order n squared, then this becomes order n squared, n cubed, or not n cubed. Come on, all the way. Get rid of that, sorry. N to the fourth plus n to the third, which is going to be order n to the fourth, right? Which is, of course, terrible, very terrible, right? But that's the naive way of looking at it, right? First of all, do we really need to do cycle detection? Second of all, is it really all that bad, right? So let's make some observations, right? The naive implementation means that you're going to have order n to the fourth. But let's make the first observation here. When you perform DFS, you're performing it on a very sparse graph, right? In fact, you're performing it on a forest. Right? Let's go back to the algorithm over here and remind ourselves what it looks like on another tree here, the tree that we were actually working with. Where's my weighted tree? Oh no, where is it? Is there MST? Graphs? Oh, what happened to my weighted tree that I was working with last time? All right, fine. We'll find you over here. There it is. All right. I'm going to go ahead and delete everything here. Right. Remember that was the order, right? Actually, no. Let's undo that. Right. That's a tree, right? I don't remember what the last thing that we added was, but I think it's probably this thing, right? And then we would have added maybe this thing, right? That's a forest, right? That's a forest, right? In other words, it's a very sparse graph. Right? Sparse graphs mean that M becomes order n, right? Let me put that down as an additional note, right? It's a sparse graph. A sparse graph means you don't have many edges. In other words, order M is going to be order n. Sorry. Go back. There we go. That's what I meant. Right. Means I'm bad at typing anyway, so there we go. So a sparse graph means that you don't have many edges. In other words, M turns out to be linear with respect to n. And so the DFS simplifies, right? DFS then becomes not M plus n, it becomes n plus n. And that's going to be order n, and that takes it all the way down to n cubed overall, right? And the sorting operation is going to be n squared log n, right? So it's not that far off, right? There's another way of doing it though, right? Another potentially better way, is to not do cycle detection. Instead, use a smart data structure. Right. So a smart data structure in this case is going to be something somewhat familiar, and it's going to be trees, but it's actually a completely new operation that you've probably never seen before. It's called a disjoint set data structure. Yeah, go ahead.
Do we have to see if it's a sparse graph before we do DFS?
You know that it's the graph that you're building is a sparse graph, right? I'm going to add an edge to this graph, and I'm going to ask, does that induce a cycle, right? Well, you're building a tree, right? And so if you've got this forest, right? And if you ever add an edge, you either make another larger forest, or you make you induce a cycle. But in either case, you're never going to add more because of the entire loop itself, right? Let's look at the main loop again. There we go. Well, the edge set is less than n, right? You will never have order n squared, otherwise you break out of this loop, right? So it's going to be sparse no matter what, right? But a disjoint data set has a very, very particular purpose. Now, in all honesty, I've never actually seen this used outside of Kruskal's algorithm. So it's a very, very limited use data structure. But the purpose is that you maintain a collection of disjoint sets. So if you've got a collection of elements, you're putting them into different sets such that the intersection of any two of those sets is empty. In other words, an element A is not in multiple sets. All right? It's in one set and one set only. Sets are going to be represented. Then the overall, what you're going to do is you're going to combine these things until you've got one set. So if you start out with 5 sets, you combine them until you're down into one set. Okay. Sets are going to be represented by nodes and trees of nodes, but there may be an arbitrary number of children. So we're not talking about binary trees. Right? You can have 3 children, you can have 4 children, you can have 1 child, you can have as many children as you want, right, on one node. We only maintain a reference to the parent, not the children. Right? If we maintain a reference to the children, then that would kill our efficiency for this data structure. Right? Each set then is identified by a representative, right? The root of the tree. I have a visualization over here to show you what it looks like. Right? Now, in this case, there are 8 elements numbered 0 through 8. So sorry, there are 9 elements numbered 0 through 8. There are 3 disjoint sets. The tree represented first by this one, the tree represented by this one, and the tree represented by this one. Now, for each element in the tree, its representative is the root. For example, 0 and 3. Right? 0 has a representative of 3. 1 has a representative of 3. 3 has a representative of 3. So to ask, now you can ask some questions. For example, you can ask, here's an element. What's its representative? Here's two elements. Are they in the same set? All you need to do to determine that is, do they have the same representative? For example, is 2 and 5, are they in the same set? Right? So what you do is you find the representative of 2, which is 3, the representative of 5, which is 6, and you answer no. Right? Okay? The way that you did that is you jumped to the node representing that value, and then you traversed all the way up to the root. You found the representative, 3 and 6, and you said, nope, they're not in the same set. Yeah?
Would you need random access to them?
You need random access to the nodes, and we'll get to the implementation here in a second. Right? Finding a set, right? Well, who's the representative of, say, 4? Let's go with 0, sorry. Well, you start at 0, and then you work your way up until you get to the root, and that's its representative. Ooh, what did it do on the way up? Did you notice what it did? We'll revisit what it just did in a second. Basically, it collapsed the tree. Because as I go up, what I'm going to do is, all right, well, I need to find the representative, but at the same time, there's no reason for me to be deep in the tree. I'm going to collapse the tree so that it's more efficient. Right? Imagine if this was a really long tree. Right? Let's draw this disjoint set out as a really long tree. In other words, it's no better than a linked list. If you start down here at the root, and then you have to go all the way back, or down here at a leaf, and you have to go all the way back up here to the root, this is going to end up being order n if it's just a regular old linked list. So in other words, we're going to want our trees to be shallow. To keep them shallow, every time we ask a question, we also modify the tree to make it shallow. Right? Let me go ahead and, let's see, initialize. Let's see, 50, we had 9 elements before into 3 disjoint trees. So let me go ahead and redo this. None of them are deep enough. All right. Oh well. Examples, 3 disjoint trees, default. Yeah, there we go. This is what I started out with, right? Now, once again, let's go ahead and find the set of 0, right? Now, before I execute this, note what's, I guess I could have rewound it, right? Again, what is it going to do? It's going to find 0, and then it's going to traverse back up to the root, but at the same time, it's going to say, I don't need this long sequence of nodes. I can go ahead and attach myself immediately to my representative. And that's what happens. 0, 2, 3, 0 comes up to be the new a new child of 3. That ensures that all of these trees are going to be very, very shallow. And if they're very, very shallow, it's extremely efficient. Right? You can ask the same question again of, is 1 in the same set as 4? Right? You only have to have 1, 2, 3, 4 comparisons, and then answer the question yes. Right? So this seems like, oh wow, this is kind of a cool data structure. How would we go about doing these operations? Right? Well, the first operation is, of course, to initialize a node. Right? Initialize all the nodes. We're going to create a single node tree where U is the representative. Right? So it's its own representative. U is checked to make sure it is not part of any other tree already, right? And then we will maintain random access to each node so we can jump to the node in any particular tree. Right? As you asked, if we have to go finding the node, then we're back to linear search. So each node is going to have, you're going to be able to jump to that node. If I say find 0, right, you can jump to the node representing 0, okay? That's what this looks like initially, right? So if we started out with 8 elements, everything would be its own representative, everything would be in its own tree, everything would be in its own set, right? We'll understand why this is applicable to Kruskals in a little bit, right? But hopefully you can see it along the way here. Now, what are some other operations that we're going to want? Well, find set, right? It's going to return the representative of the set containing U. We saw that in action. You jump to the node U, you go all the way up to its root, and that's its representative. Right? So once again, to visualize that over here, let's restart with, I don't know, 4 disjoint sets for something new. And find set of 11. Right, there we go. And all it does is goes up, and 5 is the representative for 11, right? Okay. That's easy. And are they in the same set, right? So it returns true if both u and v are in the same set, i.e. in the same, they have the same representative, i.e. they're in the same tree, right? In other words, it just calls that other method twice. And if they have the same representative, you answer yes. If they have different representatives, you answer no. Now here's where the real meat comes in. Sometimes you're going to want to take a union of 2 sets. I want to take, say, this set over here, and I want to union it with this set over here. And so in terms of trees, I want to combine these trees. Right? Let's talk about how that's done before we visualize it. Here are the essential details. When you're unioning 2 sets, we always attach the smaller, that is smaller in terms of shallower tree, of the 2 trees to the larger, in other words, deeper of the 2 trees. Right? That, along with some complex analysis, is going to ensure that we have a very efficient data structure. And we'll talk about that in a moment. The optimization step here. Every operation that traverses up the tree, in other words, find set and same set, and because it uses find set, make sure that you are collapsing the tree. You're taking advantage of the tree traversal to also collapse the tree at the same time. Okay? So those are the essential details. Let's come over here and take a look at what it would mean to say union, I don't know, 0 and 7. There we go. So let's predict what this is going to look like. 0 and 7. First of all, 0, you find it, and then you find its representative, 3. All right? 7, you find its representative, 5. Right? You've got these 2 nodes. Now I'm going to attach one of them to the other. This one is deeper. Right? It is of depth 2, right? 1, 2. That's captured in this R value right here called the rank. Right? So this has rank 1, rank 2, excuse me. And this over here also, I don't know why it says it has rank 2. It should only have rank 1. It doesn't matter. But anyway, this one is the shallower one, right? Because it has depth 1. So we're going to attach this set to this set over here. We're going to do that using the representatives. 5 is going to become the a new child of 3 over here, right? Let's go ahead and watch it. Again, 0, you find the representative, right? And you took advantage of that traversal at the same time to collapse it a little bit. And, it looks like the deeper, okay, so the R2 and R2, you break ties arbitrarily. So I don't know why it said that it was rank 2, but it doesn't really matter, right? As long as you are consistent about it. So in this case, 3 became the new child of 5. If 5 became the new child of 3, I guess it wouldn't really matter. It'd still be a depth 1, 2, 3 tree, right? Okay. Let's search for 10. Predict what's going to happen there. Find set for 10. That's the deepest one. So as we go up, we're going to collapse that tree a little bit further and make it a depth 3 tree into a depth 2 tree. Right? Find 10 up there, and actually the entire thing becomes everything all the way up becomes a child of the new ones. All right. Let's reverse that. Can I reverse it a little bit? There we go. All right, and I'm going to go step by step here. All right, we found 10. We find its parent 4, and 4 is not a child of 5 either. 3 is a child of 5, so we could collapse 4 and 10 at the same time. And it does. Right? 4 and then 10 as well. Right? This collapsing as you go along ensures that the trees are always going to be very, very shallow. Okay? All right. So what does it get us? Again, it goes beyond this lecture at least, maybe not this course, but this lecture, to show that the efficiency, of course, depends on the height of the trees, which is going to be at most log n. Right? Now, if you do a full amortized analysis, basically the overall cost of starting with n disjoint sets and unioning them until you have one set is order n. Right? The overall amortized cost. Right? Unioning is not a word, isn't it? I'll go ahead and hyphenate it to make it a word, right? So it's only going to be order n. Okay? Now, how does that help us out with Kruskal's algorithm? Let's come back over here to the pseudocode. Right? If I don't actually have to, if I don't actually have to do cycle detection, right? How could I use a disjoint union data structure to determine whether or not something would induce a cycle? Right? To understand that, let's go back to the original graph here, okay? And erase this, erase this, erase this, okay? So initially, what are my disjoint sets? My disjoint sets are each one of these vertices, okay? Now, I'm about to add another edge, this one, in order, non-decreasing order. I ask the question, are these two in the same set? If they're not, then I know that adding this would not induce a cycle. So go ahead and add it, right? Let's continue that way, right? This one is in some set, in its own set with its own representative. This one is in its own set with its own representative. So adding this edge would not induce a cycle. Right? And fast forward here to something that looks, that's a little bit more interesting. 6, what's next? This one, 7. There we go. 7, right? So actually, no. Let's look at this. There are now 1, 2, 3 disjoint sets. I'm about to add this one. This one is in one set. This set over here, and this endpoint is in another set. This set over here. So in fact, I end up adding it because they're in different sets. That takes the disjoint sets down to 2. Right? Now I'm about to add another vertex here, or another edge. This one, right? Question mark. Do I add it? No, because doing so would induce a cycle. But I don't ask the question, does it induce a cycle? Right here. I ask the question, is this endpoint and is this endpoint in different sets? And they're not, because this is all one set now. This is one set and this is another set. So this is how I can use this for Kruskal's without answering the question of does it contain a cycle? Now the unfortunate thing is, does it buy me anything? Right? Let's come back over here to the pseudocode. Right? So I still have to do I still have to do sorting, order m log m. Right? That's not. I'm not going to get out of that. This one is still order m. But now instead of asking the question, is it acyclic, I ask the question, are the endpoints of E sub k in 2 different sets? Right? Now, amortized over the entire cost of the algorithm, that's going to be order n, right? Okay. So one way of looking at it is going to be order m times n, which is right back to order n cubed, right? But you have to understand that that's the amortized cost, right? Amortized as in it's going to be order n over the entire algorithm. In other words, you do not multiply. What you do is you add, right? So it's going to be order m plus n, which is order m. Right? So it ended up buying me something, order n squared, at most. Right? So using a disjoint set is going to improve the efficiency of this algorithm. Now, when you actually go to program this, and if you choose to use Kruskal's algorithm, do you want to use a disjoint set or not? It depends on whether or not you want to implement it. I will give you a preview here. Okay. I'll restart that in the background here. And I'll... nope. There we go. If that comes up in a reasonable amount of time, I'll show you what an implementation would look like. The obvious question first would be, is there a disjoint union in Python? No, not that I know of. You could probably find an implementation somewhere, but whatever, right? But in any case, what my recommendation is going to be, you know, it's not that going to be that much more difficult to ask whether or not something is acyclic, right? You're doing that anyway as part of your as part of assignment 7. You might as well reuse that code as part of assignment 8. Right? Hopefully this comes up. I worked really hard on that implementation at one point, so it'd suck if I wouldn't be able to show you too. There we go. Disjoint set. Yeah, go ahead.
So when you mean amortize, you mean like adding every node to the set?
Sometimes it costs a lot. Because if it's really deep in the tree, right, then that's going to cost you. But at the same time, you're flattening that tree, so you're using that to make future operations less expensive. So if you do a worst case analysis of this, then you come up with sometimes it costs a lot, sometimes it doesn't cost a lot. But if you average it out, it's going to be order n. Right? Yeah.
So for assignment 8, if we use the acyclic version, it would really add a big enough of the result.
No, I mean, I think that the largest graph that I give you is maybe 20, 30 nodes or something. Yeah. Yeah, it's not gonna. I mean, you're talking about millions of nodes before you see a difference, right? Okay. So here's my disjoint set implementation in Python. First of all, you need node representatives, right? And the node representative is going to have an item. The ID is its representative, right? The root, right? And then also the rank, right? This keeps track of, they don't call it depth, they call it rank because it's an estimate on the depth or the estimate on the height. It doesn't need to be exact. You just need a criteria for when you combine two trees together. Do you combine it, this tree and you attach it to this tree, or do you take this tree and attach it to this tree? And you always attach, remember, because I don't, when unioning two sets together, you always attach the shallower to the larger. If you did it backwards, the amortized analysis would fail and it would actually devolve into order n squared, because then you're talking about a linked list. And if you always have to traverse down to the end of the linked list and you're doing that over and over and over again, then that's going to compound and give you order n squared. Right? So and then finally my parent. I don't keep track of the children because you don't need to. Right? In fact, if you kept track of the children, it would probably kill your efficiency because you'd have to update them all. Right? Is root? Well, that's just if your parent is none, then you are the root. And then I've got a toString method right here. Okay. We initialize. Again, your observation of do we need random access? Yes, we do. And so what I do is I put these things into a map. Right. I map the element that of items. Let's see. I map the item to the node that holds it. I create a disjoint set node holding the item with a representative with a rank of I think. Right. No. What is that? What is the second one? ID. Everything is its own ID, right? And then I put that into the map so I can immediately jump to it. I've got a toString method here to make it look nice when I show you how it works. Find set. It returns the representative, which is always going to be an integer, of the set of the given item. Right? As a side effect, if possible, it will collapse the path back up to the root all the way. How does it work? Well, it's this private method. In Python, there are no private methods. So the way that you get privacy in a method is by prepending an underscore. And that's basically an advertisement. Don't mess with this function. Don't call this function. It's internal. It's supposed to be private. But Python does not have the private keyword, and so it's not enforced. Right? It's just a convention. Right? So how does it work? Well, we start at the current node, and I'm using my map here to get the current node of the item. Right? While there is a parent, traverse up and we find the root, so that we find the root node. We do the same thing again, collapsing as we go along here. So if I've got nodes as we go along, right? If I've got node, going to node, going to node, going to node, right? Then what and this is my thing. This is my thing that I'm searching for, and this ends up being the representative, the root. What I'm going to do is I'm going to collapse, and then I don't need to collapse this one, so that we end up with R, and this is A and B and U. All right, we'll end up with A and B and U. It collapses the tree as you go along. All right? And that's all that this code is doing right here. Right? It does another traversal up, collapsing. And then it returns the root node. Right? And then we get the ID, which is going to be the representative of that thing. So you're finding a set of a particular item. Right? Are they in the same set? All you have to do is find that set. And if that's equal to that set, then you return true. What about taking a union? Again, here it's a little bit more complicated. You find the representative, which is the root node, and then you ask a question. First of all, if they're already in the same set, you don't collapse, you return false, because returns true if the operation had an effect, false otherwise if A and B were already in the same set, right? You don't if I have A and B in one set and I take their union, it has no effect. Otherwise, depending on the rank, I make one the child of the other or vice versa. Right? And that's just a bunch of parents and ranks, and you're changing the ranks here. This is why the rank is an estimate. You just, if you're combining two sets, you add the ranks together, and it's just, it doesn't even need to be updated. In fact, it won't be updated. It would be inefficient to update it, I believe. Right? All right. So here it is in action. I create these words. The words are just A, B, C, D, E, F, G, right? And then I create a new disjoint set out of it, and I print it. Let's go ahead and get rid of the rest of this and reveal it as we go along. There we go. Come on, lecture. CSCE 3, 11, 10. There we go. Python disjoint set. Come on. There we go. A, B, C, D, E, F, G. Right? 7 items. That would be like starting over here. Initialize 7 items into 7 sets of rank 0, right? Or rank 1. That's where we've started. Right? Now let's do various operations. So I want to know what the representative of the set A is. Well, that's going to be 0, right? And so it'll output 0. Oops. It'll output 0. Okay? Let's go ahead and union A and B together, and then print out the resulting tree or whatever, the disjoint set. Right? A and B are now in the same tree. Over here, that would correspond to unioning 0 and 1. And again, you find those two, and it doesn't matter in this case because they're going to have the same rank, but it looks like that A ended up as the child of B. Right? Over here, let's do it again. Let's go ahead and do B and C now. So we'll have A, B, and C all together. And we see B goes to A goes to none, and C is C's parent is A, and that goes to none. So B and C both have a parent of A. In other words, we've got A up here, and then B and C as 2 children. Over here, that corresponds to, again, unioning, what did I say? 1 and 2? Yeah, 1 and 2. There we go. Find the representative, and 1 becomes the child of another. Right? Union D, E, and F together. Right? Now, all of these are independent, so it's going to create yet another tree that basically looks like the other tree. So DEF would be 4, 5, 6. So union 4 and 5, right? DEF? Oh, okay. That doesn't matter. I just don't know my alphabet. And then, yeah, it's because it's at 0 index. So 5 and 6 here, and we've combined. There we go. That's what it looks like so far over here in Python. Last one. Let's go ahead and take those 2 trees with 3 elements each, and let's go ahead and union those together. And what does it look like finally? Right? This. Right? Or visually over here, it looks like union, say, 0 and 6. There we go. It's going to find the representative 1, find the representative 5, and then 1 becomes the child of another. Right? There we go. Note there that that did not collapse the trees. Right? Only the other operations of, say, find set of 0. Predict really quickly here what's going to happen. 0 is going to end up becoming the child of 5. There we go. Predict what would happen if I combine 3 and 2. So first of all, when I find 2, right, it's going to find 2, it's going to find 1 and go up to 5 to its parent, to its representative, meaning that it got collapsed at the same time. Right? Then it finds 3, it's its own representative, and so 3 becomes the child of 5, and I think that this will end up with one set. All the children are going to be at the same level. Find 3, find 2, collapse at the same time, right? And then 3 becomes the new child of 5, making this extremely efficient because it's all shallow, right? And there, now we're done with Kruskals, right? Because we combined all these sets into one big giant set. Cool. Again, it's a nice data structure, but it's like a one-use data structure, right? It doesn't really buy you all that much except for Kruskals. I've never seen it used anywhere else. In fact, is there any information here? Exploration mode, e-lecture mode, no. Examples, I don't know. Union find, model collection of disjoint sets, determine, yeah. And hence can be used as part of Kruskal's algorithm from MST. So if you can find one other use for disjoint sets, please let me know. Or if you out there in YouTube land know of any other use for these things, let me know. Yeah, go ahead.
Kruskal make?
That's a good question. To answer my question, I guess you would go back to the original Kruskal paper and see if okay, well, here's how you can do it efficiently with a disjoint set. And if so, maybe they just made it for that one algorithm. Or if they said, well, there's this other paper that's responsible for this disjoint set data structure, then you jump to that paper and, okay, well, what applications did they identify for this thing? That's a good way of answering it. I might do that if I've got time. Otherwise, there's another, actually there are about half a dozen minimum spanning tree algorithms, but here's another one, prims. These are all named for the people that came up with them. It works by starting at a single vertex and building a connected tree outward. So with the rest of our time today, let me just go ahead and show you what that would look like on a particular graph. And unfortunately, now I'm really going to have to find that graph. There's the graphs. Do I have MS? Nope. Used. I want a weighted MST. There we go. All right, there's the same one. Okay. So I'm going to use a highlighter on this because the way that prims works is by starting at a particular vertex. Now, it's an arbitrary vertex. You can start anywhere you want. You'll come up with another equivalent minimum spanning tree. So what I'm going to do is I'm going to start at A. Right? There's my tree so far. Now what I do is I look at what are called the fringe edges. The edges coming out of the tree that I've built so far. I see 7 and I see 5. If I'm being greedy about this and I want to build a minimum spanning tree, then my choice is clear. I take the minimum weighted edge. And now I've built the tree out further. Here's my tree. Actually, I wonder if I can get, if I highlight, does it fill in? No, it does not, darn it. All right, now if I fill that in, nope, never mind. All right, there. You get the idea. There's the current tree now. The tree consists of 2 nodes, 2 vertices, and 1 edge. But my fringe, my frontier, has changed. Here are all of the edges going out of the frontier now. 7, 9, 15, and 6. So again, if I continue with my greedy choice and choose the minimum each time, what do? 6. And build out my tree even further. Now again, my fringe vertices, my frontier vertices have changed. 7, 9, 15, 8, and 11. As I go along, I'm keeping and maintaining this list of fringe vertices. Right? What's the minimum? 7. So I expand out here to this one. Guess what happened to those two other vertices, two other edges, excuse me. 9 and 15. Yep, they're no longer part of, actually 15 is still, but 9 is not. 9 is no longer part of the fringe it's now entirely within the tree now, right? So I would end up throwing it away and not considering it. My fringe edges are all right here. Let me go ahead and rewrite 15 over here so that you see that it's still there, right? And so once again, I make a greedy choice, and now I've got 2 choices, 2 8s. Oh, sorry, 7. I don't have 2 choices. Thank you. All right, 7, and I choose that one. And now I've brought in E here. Now that 15 goes away, right? And I've got fringe vertices up here. I've got fringe edges down here. And I make my choice yet again. What is it going to be? 5. There's my tree now. This one disappears from my consideration. And lastly, I've got 9 giving me this one right here. So it builds outward from one particular vertex, right? Now the questions that we're going to resolve next time are, well, let's write some pseudocode for it, but what is the most appropriate data structure to keep track of all this? Let me go ahead and rewind here. And at this point we were at, here, let's go rewind back to this one, right? How do I maintain this frontier of edges? Right? What I want to do is I want to, if I discover a new edge, I want to put it into that data structure efficiently. But also, which one do I pull out on my next choice? The minimum. So is there a data structure that allows me to put stuff in efficiently, pull out the minimum efficiently? What kind of data structure does that sound like? Min heap, exactly. So if we use a min heap to keep track of all these fringe vertices, it's going to be very, very efficient. We'll cover that next time, though. Any other homework questions? Still have it up? Yeah, go ahead.
Yeah, so for number 2, the one we write pseudocode, is that? It's 2.
Yeah.
Do we have to assume that it might be disconnected and it might be multiple cycles?
Well, I mean, you can, whatever assumptions that you've got, let's see. DFS can develop an algorithm that given a graph and 2 vertices determines if X and Y are connected by a cycle or not, right? So, I mean, if you use DFS to say that X and Y are not even connected by a path, then certainly there's no cycle. So if you want to take care of that as an edge case to begin with, that's fine. But I think that you could probably, subsume that with an overall algorithm if you ask the right questions of DFS. Right? Pseudocode, an analysis would be good because, I mean, if you all you need to say is something like, well, observe that DFS is order m plus n, and we perform it k times, right? K times, then it's going to be order k m plus n, which is right back to order m plus n. No worse than DFS. But if your analysis says, oh, you do it n times, right? Then it's going to be order nm plus n squared. Leave it like that, or simplify it if you want to, order n cubed, right? Something like that. I mean,
Do we have to do it in times?
it depends on your analysis. I'm saying, suppose that your analysis came up with this, right? Because I don't want to say you're only going to do it this many times, right? Because then I'm giving you the answer about what you're going to do. Right? Say what? You should do the analysis. This is problem 2, where you have to adapt DFS or use DFS as a subroutine to determine whether or not X and Y are on a cycle. It might help to think of an example, right? For example, the examples that we've been looking at are probably going to be trivially true. Come on. I don't know. I just need to hear a random graph, right? Every edge is going to be sorry. every edge is going to be on some cycle here, right? But if I drew another one, say X over here, are I and X on a cycle? No, right? What if I have a disconnected graph, Y and Z, right? Right? Are A and Y on a cycle? No, right? So, are A and H on a cycle? Yes, they're on many cycles. There's one, there's another, right? A and H. Right? So you just have to answer whether or not they're connected by a cycle or not. Right? In other words, think of the question like this, right? Are there at least two paths between X and Y, right? So you can use DFS to answer, is there at least one path, right? Because are they connected, right? Now, how can you modify the graph, change the question, adapt DFS something to ask the question, is there a second path that is distinct from the first path, right?
So
Yeah.
original DFS, the DFS we did in class, that does not assume that does not include the case where it's going to be disconnected.
I mean, if it's a disconnected graph, then the question is there doesn't even exist one path. So you can immediately say, no, there's not two paths, right? So you can still answer the question for a disconnected graph. Okay.
But on problem 5, where we have to do the
Problem
problem 4.
4.
Because sometimes you give us a disconnected graph. So do we?
Yes,
start-
yes.
So after we do a DFS on the first part,
You'll have to restart it, DFS, yep.
so do we restart on like the next minimum node?
Arbitrary. Yeah, next least weighted node or next least numbered node,
Okay.
right? Whatever. Whatever's the easiest, I'd say. Yeah. And is it connected? Does it contain a cycle? And then BFS, DFS ordering. Those are the only things that you have to output. Now, once again, you can use network X to represent your graph. You can use network X built-in algorithms to check your solutions. For example, when you do a minimum spanning tree next week, you can run network X's minimum spanning tree and check, do you get the correct number? But you still need to provide your own MST implementation. They probably have a DFS traversal of some sort in network X. You can use it to see if it's connected. You know, you can ask whether or not there exists a cycle or whether or not how many connected components there are. But you still need to have your implementation, right? You could just use that for testing purposes. Right? In fact, if you want to put it in the output, my output says that there's one connected component. Network X says that there's one connected component. We must be correct, right? Something like that. All right. I'll see you on Friday.